second part of our two-part lecture series on Bayesian computations, and I am Arnab Chakraborty from Indian Statistical Institute. From the first part, you will recall that we have learned the following concepts. We have learned about Bayesian statistics, the main principle of Bayesian statistics as the optimum way of combining past experience with our present information. The past experience was called prior distribution, the present information is more commonly known as the data, and the future information that you create, the information that you create for future use, that is called the posterior distribution. In other words, Bayesian computation was like a box, a machine in which you fit in the prior distribution and the data, and both these pieces of information are hashed together to produce information for future use, which we call the posterior distribution. And you also learned that even if we work with simple prior and simple data, still the posterior may be rather complicated, and this is one example of a complicated posterior that we have also seen. So, this posterior distribution is actually a probability density f mu tau, which is a very complicated formula involving two parameters mu and tau, and the xi's are our data points, and you will see that it is a fraction. The numerator is that complicated expression and the denominator is integral of the entire numerator. It is not at all easy to compute that integral directly. Here we are having a double integral because we have got two parameters. Now, the best way of visualizing such a complicated posterior density is as a surface, and that is what I am showing in this colored surface here. So, here this matte colored red rectangle, the flat rectangle on which the tent like thing sits. So, this one is the parameter space. So, this is mu direction and that is the tau direction, and here you see the posterior as a surface. So, wherever this has a peak, this means f mu tau has a high value. Wherever this falls off, this means f mu tau is becoming smaller. The total volume under this surface equals 1. Of course, in this case we have only two parameters, that is why we can afford the luxury of plotting the surface. If we have 3 parameters or more parameters, there is no simple visualization tool, then we have to deal with it completely mathematically. Now, our aim is to simulate from this posterior distribution. By this we mean that we are picking lots of random points from this reddish rectangle here, they will look like this, and wherever there is a peak, this orange region, you will see that there are lots of points concentrated over that region, and in the low lying green regions you will have hardly any point. So, the density of these points closely mimic the shape of the surface. This is what we are trying to get from this complicated formula. Now, the most popular way is using a technique called Markov chain Monte Carlo, a rather impressive name. Indeed, in its full generality, it is pretty complicated. However, you will be surprised to know that even this complicated thing is known to almost every child. We always use it for one particular purpose even from our childhood, and that purpose is nothing but card shuffling. Suppose I take a deck of cards and I want to shuffle it. Then what do I want to do? I have these 52 cards and I want to shuffle it. This means I want to create an arrangement that is perfectly random. Every arrangement is as likely as every other arrangement. Now, one simple way of doing that is to just scatter all the cards on the floor, then start picking them up one by one at random. We never do that. Instead, we shuffle. So, this is how the shuffling typically goes. You take the two halves and then you just mix them up. Now, when you mix them up, what do you get? You get a partially mixed up deck. Suppose something like this. It is not that you have completely mixed them up yet, because the order of these cards is still the same as the original order. The order of this part is also same as the original order. So, you have mixed it, but only to some extent. You have injected a little more extra randomness in the deck. Then you just mix it up and again you perform the same shuffle that injects a little more extra randomness. The shuffling injects randomness step by step, and that is exactly what any Markov chain Monte Carlo does. Card shuffling is an example of Markov chain Monte Carlo. You just mix things up a little bit at a time and you keep on doing it as many times as needed to make the entire thing completely random. For example, it is known that you need to perform at least 7 shuffles before the deck becomes completely mixed up. In case of more general Markov chain Monte Carlo, this stopping criterion is much more complicated, but let us first try to understand how we use this idea in case of our example. So, this thing that I am going to talk about now is a special example of Markov chain Monte Carlo. It is called the Gibbs sampler. If I present it in its full mathematical glory, it might scare you away. So, let us first look at it from a pictorial viewpoint. That is the best way of understanding Gibbs sampler. So, here we go. So, here is our familiar posterior density, that complicated hairy formula. We are now visualizing it as a surface, and you have already seen that this reddish rectangle, that is our parameter space mu and tau. Every point on that reddish rectangle gives you one parameter combination, one value of mu and one value of tau. On this sits this tent like surface, the green surface, the posterior. We are trying to get lots of tiny little dots like throwing darts on this red flat plane, such that more points are concentrated near the peak, less points near the low lying regions, following exactly the pattern of this surface. Here is how Gibbs sampler will proceed. You first start with a little tiny dot anywhere in your parameter space. Notice carefully, you will see that there is a little tiny dot over here, that is our arbitrary starting point. You can start from any point, just as when you do shuffling you can start irrespective of whatever is the original configuration of the deck. So, you start with any arbitrary point. Now, starts the drama. You imagine a vertical plane. So, here is your surface, you cut the vertical plane, you section the vertical plane like this, such that the vertical plane passes through that point and is also parallel to the mu axis. So, here is your surface, you just pass a knife vertically to cut the surface parallel to the mu axis. This cuts the surface along a curve. Notice the purple curve, it cuts the surface along that curve, and also it cuts out a straight line along the parameter space. Now, we are going to move from this blue dot to some random point along this line. We are going to move along this line. What does that mean? Since this line is parallel to the mu axis, we mean that we are keeping tau fixed and changing only mu. Tau is remaining fixed, only mu is changing, and we will make a random step. That random step will be determined by the shape of the purple curve. Wherever the purple curve peaks, you have a high probability of moving to that point. For example, you have a high chance of moving here or rather low chance of moving here. It is possible that you can move here, but you will do so only with a very small probability. So, I am going to move randomly following this curve along this line. So, I get some random point. Well, in this case it turns out to be this, which is quite natural in the sense that this is where the curve has a pretty high value. So, you have got your next point. It is just like you have performed your shuffle one step. it is a little bit more random than the starting point. The starting point was arbitrary point, it was a fixed point, you just fixed it arbitrarily. This one has a little bit extra randomness, mu has been randomized to a little bit, tau has been remaining fixed. So, this is like the position of the deck after you have made one shuffle. Now, we come to the next shuffle. Now, what you do is you again section the surface vertically, but this time the sectioning plane is parallel to the tau axis. Same old story. This marks out a curve, a purple curve along the surface and also a straight line along the parameter space. We are going to move from our current position, that is this blue dot, along that line, which means now mu is held fixed and tau is changing randomly. Again our step will be a random one. Where we land will be governed by the purple curve. Wherever the purple curve peaks, you are more likely to put your step there. But it is random, so it is possible with a very low chance that you possibly land somewhere where the purple curve is low. It is possible, but as I said, very low probability. So, here is one possible move that I have made. I have moved along this line, well, I am more or less under the peak. Now, I am going to repeat it again. So, this was the original configuration, you moved once, you moved again. Now, I go back to the original direction. So, I again take a vertical section again parallel to mu through my current point and I plan to move along the line determined by the cross section of the vertical plane and my parameter space, and I will move following the purple curve. So, the random step, suppose it comes here. So, you see how we are moving in a zigzag fashion, first parallel to mu axis, parallel to tau, again parallel to mu, and you get the general idea. We keep on doing this. Now, again we will do it parallel to this axis and we go on doing this. As we are doing this, this point is becoming more and more and more random. Think of it as I am shuffling a deck of cards. I started with this configuration, shuffled it once, I got a slightly more random point, shuffled it again, got an even more random point, even more random point. I am injecting randomness step by step until I have accumulated enough randomness, and when enough randomness is accumulated, then I will get a random point which will be following this posterior density very closely. So, observe that in a Gibbs sampler, that is called the Gibbs sampler, this particular technique, I am moving in a zigzag path. I am first moving horizontal, vertical like this, possibly I am starting from here and I go on and on and on and on, and then when I believe I have made sufficiently large number of steps, so I have been really random, then I pick only the last point. It is again like shuffling a card, shuffling a deck of cards. When I am shuffling again and again and again and again. I only keep the very final configuration, not all the intermediate configurations. Similarly, I throw away all the intermediate points, I take only the final point which is believed to be sufficiently random. Of course, in this case I was working with only two parameters. So, it was a two dimensional thing. This is perfectly general and may be done in any number of dimensions. For example, if we are working in 3 dimension, then this path will look like a maze of water pipes, first parallel to x axis, then parallel to y axis, then parallel to z axis, then this xyz patterns keeps on continuing, and after this thing is sufficiently complicated and random, you stop and pick the very final end. So, that is the technique by which you generate one random observation from the posterior distribution using the Gibbs sampler. So, we noticed that the Gibbs sampler does not sound particularly easy, in the sense you have to do so many steps in order to arrive at only a single point. Here, for example, I have to generate so many different points in order to come at the final point, which is the only thing that we keep. It is just like shuffling a deck of cards. You have to shuffle it a number of times before you have mixed up the deck completely. It is not that you shuffle it once and it is done. Similarly, for Gibbs sampler. Now, the amount of time, the number of points that you generate and finally discard, that has a name, it is called the burn in period. That is the amount of time that you have to spend until this randomness kind of burns in. So, now it starts to burn fully, it is then that you stop the process. So, you have to throw away that many points before you get the first point that you are going to use. Now, of course, it is not enough to get a single point from the posterior distribution, you need a pretty large sample from the posterior distribution. Even to get a single point, you have to carry out all this complicated procedure. In that case, how do you actually get a large sample? Well, one simple answer is you repeat the entire thing again and again and again and again, starting with some arbitrary point every time. You may start with the same point every time, there is no problem. So, here is like the schematic. You want to generate say 5 samples, then you start from some arbitrary points, go on and on and on, then when you get sufficient randomness, you stop. So, you get 1 point from the entire chain. Again you start it on and on and on, you get 1 point and stop, and you are repeating it 5 times. Every time you have to throw away that burn in period number of observations. That is somewhat wasteful, because the burn in period may be something like order of 1,000,000 observations. Of course, with a computer that is not much, but if you want to generate something like a sample of size 1,000,000 and throwing away 1,000,000 observations in each of those 1,000,000 cases, well, that is a bit stressful even for a computer. So, sometimes people prefer a less wasteful technique, which is just continue to run the same chain. So, you have first generated all these things and picked that thing. So, you skip the burn in part and you have picked one, then do not start afresh again, keep on continuing from the point that you have already selected and continue running the chain. But of course, your final observations are supposed to be independent. If you just take all the observations immediately following, then there will be lots of dependence, because each point is dependent on the last point. So, you have to allow a little bit of gap for this dependence to die out, but hopefully this gap will be lot less than the burn in period. Say if the burn in period is something like 1,000,000, this will be of the order of say 1,000 or even 100. So, you skip those many observations, then take this point, skip this many observations, then again take this point. This is a lot less wasteful scheme of generating the same number of observations. So, most people will prefer this one long chain approach. This is called the one long chain and this is called many short chains. Typically, the one long chain approach is more preferable because it is less wasteful. Now, we have seen it so far from the viewpoint of pictures. Of course, this luxury of drawing a picture, making a surface, drawing these sections, all these things work only for 2 dimensions. If we have 3 dimensions or more, then definitely we cannot have any of these pictorial representations. So, then we have to proceed systematically only using mathematics, and for that the main weapon is finding what is called the full conditional distributions. Let me explain. So, again we go back to our 2-dimensional example. I have that posterior surface. We were doing this thing again and again, we were sectioning it using a vertical plane. Sometimes the plane was parallel to the mu axis, sometimes it was parallel to the tau axis. If it is parallel to the mu axis, as is shown here, you get a purple curve. Notice that this purple curve is actually proportional to the conditional distribution, or the conditional density rather, conditional density of mu given tau and of course, given the data. This thing is called the full conditional for mu. That is, full conditional for a parameter is nothing but the conditional distribution of that parameter given everything else. Pictorially, if you section it parallel to that axis, whatever curve you get, that determines the shape of the full conditional. Similarly, when I section it parallel to the tau axis, this purple curve gives you the full conditional density of tau given mu and the data. So, this gives you the shape. Of course, it is actually proportional to that particular curve. There is a constant, but the constant is really not of any importance during the actual computation. Now, again we use pictures. How do I find it out mathematically? Because computer will not understand pictures, we have to somehow feed it formula and it will give us the full conditional as another formula. Turns out that finding the full conditional is super easy. Even if your posterior is very complicated or even more complicated than this, finding the full conditional can be done just by looking at it. You do not have to do any computation whatsoever. I will show you how. Suppose in this case I want to find out the full conditional of tau, that is the conditional density of tau given everything else, all the parameters and the data mu and x. All that you have to do is highlight in the numerator the terms that involve tau. Remember that posterior density is made out of lots of factors, they are all multiplied out. Look at all the factors that involve tau. I have shown them in red. Here I have a tau, here I have a tau, here I have a tau, here I have a tau. I have also a mu here, I do not mind. If there is a tau, I will highlight it. In this term there is no tau, so I have left it black. I do not care about the denominator because it is nothing but a constant, a fixed number free of mu or tau, because I have integrated it with respect to tau and mu. So, never bother about the denominator. Focus on the numerator, highlight that part which involves the parameter of your interest. In our case, it is tau. Look carefully at the form. Do not get confused with the complication. Look only at the form and you will notice that this is of this particular form. It is tau to the power something. Do not care what that something is, whether it is 1.1 or whatever. Tau to the power something times e to the power then something linear in tau, something times tau. You see, all these complicated things I have just swept under the rug and called it something. This is the form. Think carefully. Have you seen this particular form before? Well, to every statistics student, this form should be very familiar. There is only one density in the world which has this particular form, and that is nothing but a gamma density. So, without doing any further computation, just by looking at it, you guess that this must be a gamma density. Of course, you can now work out the parameters by carefully looking at what is this something and what is that something, but that is the most trivial piece of exercise. This is indeed borne out by our pictorial representation. Look at this purple curve. It does look like the gamma density. The very familiar positively skewed form of gamma density was apparent even from the picture. Okay. So, let us now try if we can do the same thing with mu. So, now the parameter of interest is mu. So, highlight all the terms in this expression that involve mu. So, these are all the terms that involve mu. Notice this time has been highlighted again, because this is something where both tau and mu occurs. So, it was highlighted in the last example, it is highlighted even in this example. These terms are not highlighted, there are no mu's over here. Again, look at only the form and you will see very easily that the entire thing is e to the power, whatever this mess is, it is a quadratic in mu. That is the only thing you need to notice, it is a quadratic in mu. What density is there that you know of, that is of the form e to the power then a quadratic? You will immediately recognize this as a Gaussian density. So, you know that the full conditional of mu, that is the conditional density of mu given the data x and the other parameter tau, must be a normal. Look at the picture, it indeed corroborates this finding. This purple curve does look like the normal density. So, using this technique, even if it is very complicated, you can very easily find out the full conditional density of each of the parameters. Of course, bear in mind that in a practical problem you may not be able to get some of the standard distributions like normal distribution or the gamma distribution, but finding the full conditional density always remains equally easy. You may not be able to associate any standard label with it, but the formula can always be read off directly from the formula of the posterior density, even if that is a very complicated thing. So, what exactly are we doing here? So, in this case, let us look at our full Gibbs sampler for our example. I will remind you once again that in our example we started with x1 to x10 independently and identically distributed as normal, mu and variance 1 over tau. We had a prior over mu was normal, prior for tau was gamma. This cross signifies that they were independent. Then from that we computed a complicated posterior density, and the Gibbs sampler turns out to be a very simple code, very easily implemented in any programming language. You start with any arbitrary point mu 0 tau 0, that was that arbitrary blue point where we started from. Then you keep on doing the following: you move parallel to the mu axis, parallel to tau, parallel to mu, parallel to tau, which means you generate a new value of mu from that posterior from that full conditional, which is the normal distribution, starting from the current value of tau. So, at step t you are starting from tau t minus 1. Once you have come to that new point, now you start moving along the tau axis, that is you generate a new value of tau again from the full conditional of tau, but using the fresh value of mu, the value of mu that you computed just now. That is what gives you the zigzag path. You are at some point, you proceed in one direction, from that you proceed in the other direction, and you keep on moving in a zigzag fashion, and you do it a large number of times, and then you get one point which is very closely distributed as your target posterior density. Even if it is a way more complicated thing, this algorithm does not become any more complicated. Unfortunately, every rose has its own thorn, and this technique has its own problems. Problem number 1 is, I am telling you again and again, keep on doing it a large number of times until you have got sufficient randomness. How do you decide that? Unfortunately, to date there is no satisfactory method to check convergence. Remember, checking convergence here is tricky. I am not checking whether the points come closer and closer together like any ordinary numerical method techniques. I am checking if the distribution is converging. Unfortunately, there is no known method which satisfactorily does this check. People are doing lots of research, there are lots of heuristic ideas, but as I say, no satisfactory method. The second thing is, always be careful with the choice of your priors. In practice, it is found that even if you have lots of prior experience about a setup, it is well nigh impossible to codify that knowledge in terms of a nice probability distribution. So, often researchers tend to take a somewhat crooked path of choosing a prior distribution which will simplify computations without paying any regard to the need of the real life problem. Any such conclusion will be grossly mistaken even if you use a wonderful Markov chain Monte Carlo and a wonderful mathematical tool or computing facilities. But having said that, I must say that this is a very popular technique. It is very popular because it can be extended to a large number of problems. These problems come under the general heading of graphical models. So, I will give you a brief idea about what graphical models are, so that you understand where the newly learned techniques will apply. And we can show it like this arrow diagram. There is an arrow from mu and tau to x, meaning that the distribution of x involves mu and tau. Such diagrams are commonly called graphs in mathematics, hence the name graphical model. Now, even if this diagram grows further, for example, suppose I tell you that the prior of mu is not completely known, it is not normal 1 1 or anything, but that in itself involves another parameter, sometimes it is called a hyperparameter, and that second level parameter, hyperparameter, has some known distribution, then you will just add one more arrow to your diagram. So, that is also an example of another graphical model, and depending on the need you can have a graphical model which is quite complicated. Well, that is the end of this lecture. Hope you enjoyed it. Thank you.